Interesting things happen when we have multiple resistors, and there's some general things that we can say. Given two circuit elements, there are really only two ways to combine them. We can combine them in series, where every electron that leaves the battery passes through the first, and then passes through the second to get back, and there's no other options. Or in parallel, where every electron that leaves can either go through one branch, or it can go through the other branch, but it can't go through both. Two resistors are in series if there's no junction between them. That is, every electron passing through the first must pass through the second with no option. In this case, we have two identical bulbs, and we're asked which bulb is brighter. Consider two series resistors, but not necessarily identical. We'd like to find the equivalent resistance. That is, the resistance of a single resistor that placed in that place would have the same behavior, meaning the same potential drop and the same current. So we take our assumption of current, which, remember, positive current, so-called conventional current. Positive numbers come out, they go through here and go through resistor 1, go through resistor 2, and go back to the battery. Having a drop across resistor 1 of delta V1, and drop across resistor 2 of delta V2. Actually, for consistency with later, I'm going to call it just V1 and V2. Your textbook really likes delta V as a drop, which is fine, but it's often conventionally just called the drop V. And then we want the same sort of thing through here, so as to have our equivalent resistor, a thing that has replaced the two with the same effect. The current through each resistor must be the same because they're in series. Right? Remember, everything leaving the battery has to pass through one and then the other, and they can't accumulate, create, or destroy charge. The total potential drop across them must equal the BMF of the battery because to keep the flow going. So we want the same current to pass through the equivalent resistor, and we want the same potential drop across it. This becomes a little bit of algebra stuff. We want the potential drop across the two resistors has to be equal to the battery, which is equal to the potential drop across the equivalent resistor. And we can apply Ohm's law to each of these, that the potential drop across a resistor is the current times the resistor. And likewise here, and likewise here. So then we can go back to, we can take these things and plug them in here to end up down here. That I1R1 plus I2R2 is the same as I equivalent plus R equivalent. But as we argued, all of the currents are the same. So I1 equals I2 equals I equivalent. Which means I can replace I2 and I equivalent with I1. I1R1 plus I1R2 equals I1R equivalent. Of course, at that point, we just cancel out the current because we see it in every term. And we get that the equivalent resistance is R1 plus R2. This is often summed up as resistors in series add directly. You just add them. It's the easiest possible case. It's the one you'll come back to a lot. It's nice. All right, stacking two resistors together makes the whole path more resistive, which makes sense because you've got more to go through. You can extend this to any number of resistors in series by just tacking them on. So if I have three or more, I'd say that R equivalent is R1 plus R2 plus R3 plus and so on, as long as they're in series. All right, question. A string of Christmas tree lights consists of 50 bulbs, each of which has a resistance of 3 ohms. What is the equivalent resistance for that string of lights in ohms? And this really is a saying that R equivalent is 3 ohms plus 3 ohms plus 3 ohms, and so on, 50 times, so it's 150 ohms. Really is that simple. How much current in amps flows through the 25 ohm resistor based on these three resistors connected to a 9-volt battery? By the way, of course, this is a little redundant. When we say this, we could have picked any resistor because they all share the same current. But we'll do the 25 ohms because why not? Since they're in series, the same current flows through each resistor. But how much? Well, let's find the equivalent resistance. That R equivalent is R1 plus R2 plus R3, or 25 ohms plus 34 ohms plus 19 ohms, which turns out to be 75 ohms. And then we say how much current would this resistor draw on that battery. So the equivalent resistance voltage, which is the battery voltage. Oops, sorry, glitch here. So I times the resistance equivalence is 9. So I times 75 ohms is 9. So I is 0.12 amps. By construction, however, this current through the equivalent resistor is the current through any one of them. All right. Which of these is true? That bulb A is brighter than B, or that bulb B is brighter than A, or they're equally bright, or that you need more info? Well, let's answer the question empirically first. See, they're pretty dim, as opposed to one bulb, which was pretty bright. All right, so by adding the two bulbs in series, we doubled the resistance in the circuit, so we drew half as much current, and half as much current through the same bulb gives us something dimmer. Parallel. Two resistors are in parallel if they are connected at both ends, such that the electron encountering the junction can pass through one resistor or the other, but not both. Since each is connected directly to the battery by ideal wires, the potential difference across each is the same. That's going to be the most important thing. For parallel circuit elements, the potential difference across them is the same. Remember that for series, it was the current that was the same, and that's sort of the logical distinction. Which of the things is the same? For parallel, it's potential, which you might even remember as parallel starting with P and potential starting with P. We play equivalent algebra games. The current, right, I battery comes here and splits, so the junction rule tells us that the current in equals the sum of the currents out. So the current coming out of the junction, I1 plus I2, is equal to the current entering the junction. But the whole point of the equivalent resistor is that it's identical in terms of current and voltage, so that's also the current going through the equivalent resistor. I equivalent. And then we know that the voltages are the same because they're in parallel, and by construction we want the equivalent voltage to be the same. So again, using Ohm's law, we can say that the currents must be V1 over R1, which is the battery over R1, and I2 ends up being the battery over R2, and I equivalent ends up being the battery over R equivalent. So going back, right, plugging this into here, we end up with these equations, that the EMF over R1 plus the EMF over R2 equals the EMF over R equivalent. And you can see, of course, we're going to cancel the EMF. When we do that, we get that 1 over the equivalent resistance is 1 over the original resistance plus 1 over the second resistance. Summed up as resistors in parallel add inversely. We add their reciprocals. I guess it should be reciprocally, but usually people say inversely. And again, this extends pretty easily. 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. Your textbook likes to write this as that R equivalent is the reciprocal of 1 over R1 plus 1 over R2, which I think is terrible because it breaks the pattern equivalent between them. But remember it any way that you like. Note that the equivalent resistance is always less than any of the parallel resistors. That's a property of these things. That might seem a little odd that we're adding more and more resistors and yet we're getting less resistance, but actually if you think about it, it kind of makes sense. There are more paths for the electrons to flow, so they don't back up as easily, so they don't get stuck. Think of it like traffic. If you have 8 parallel lanes, it's easier to move to carry high volume of traffic than if you have 1 lane. That's basically the same idea. So, which is true? That A is brighter than B, or B is brighter than A, or that the same brightness, or that more information is needed? Well, let the resistance of each bulb be R, and let the battery's EMF be EMF. The current through A is, of course, just the battery over the resistance. That was easy. In the equivalent circuit, the equivalent current is E over 1/2 R, or twice as much. They draw twice as much current. By the way, why is that not a violation? Because this is parallel. The voltage differences are the same, but the currents don't have to be. And then the equivalent is, of course, also by junction rule, IB plus IC. So we get it's twice IB, which means that the current through B is 1/2 the equivalent current, which is 1/2 twice the initial current, which is the initial current. So they would have the same brightness. Here we ask, what is the current drawn from the battery in amps? One over the equivalent resistance is 1 over 58 ohms plus 1 over 78 ohms plus 1 over 42 ohms. Throw it in a calculator and you find out that what comes out is 0.05534 inverse ohms, which actually gets the goofy name, and people sometimes talk about it. This is the mho, the inverse ohm. Get it? It's ohm backwards. So the equivalent resistance is 1 over 0.05534 mho, which is 18.1 ohms. And then the current is 12 volts over 18.1 ohms, which is 0.664 amps. The bulbs and batteries are identical. Draw a blue circle around the bulb shining brightest and a red circle around the bulb shining most dimly. Well, what we have here is that in the first case, if you imagine one bulb, you take sort of one circuit, which is not equivalent, and you just put one bulb, then the current in this case, we have twice as much resistance as this, so we get half the current. On the other hand, this thing has half the resistance of this, and so we get twice the current. So C and D will be bright, and A and B will be dim, but they will all be, like A and B will be the same, and C and D will be the same. And this really just sums that up again.